All right, so today we will start off on slide 19. So this is the second sample size calculation. Okay, so I'll just make uh, our marker here. So this is March 22nd, 2021. So last week we had lecture on Wednesday, and then on Friday there was a automated video that we used for the material that we covered on Friday. In lecture, so we're still working through lecture set number 5. Lecture set number 5 is devoted to cluster sampling. Cluster sampling is the fourth sampling strategy that we have talked about this semester. So we have seen simple random sampling, systematic sampling, stratified random sampling, and now we have cluster sampling. For each of the approaches, not including cluster sampling because we haven't gotten there quite yet, though it is sort of intertwined, we have talked about different ways of estimating population quantities. So for example, from simple random sampling, we had the simple random sample estimate. Then we had, for example, a ratio estimate, a regression estimate, and a difference estimate. So we have different strategies for actually computing our estimates depending on or from how we collected the information. With cluster sampling, we actually use sort of like a pseudo ratio estimator when we want to estimate the population mean. So an example of this can be found on slide 10. So these estimates are somewhat like a ratio estimate. So when we don't have capital M, so where capital M is the total number of elements in the population, we can approximate, for example, tau using the estimators shown in equation 3. So this is sort of like a pseudo ratio estimator. It has a similar form anyways to what we saw before. And actually we can see another example of that when we look at the forms of the estimators given in equation 1. This is probably a better example actually. So you can see that you have a ratio of the total value of the variable of interest divided by the total number of elements that have been sampled across all of the clusters. And then you can see that our variance estimate for mu tilde c, or rather for the variable of interest, that takes the form of a ratio estimator because we have the yi minus mu hat c times mi, which is sort of like the yi minus theta times xi term that we saw in our ratio estimation approach. Okay, so in summary, in lecture set number 5, we talked about the general strategy for ratio estimation, which depends on capital M. We talked about an alternative strategy that we can use, which does not depend on capital M. And that's the terms given in number 2 here, where we use more of just a natural ratio of what we observe from the clusters that we sampled. Okay, and then on Friday, what we talked about was effectively just what happens when the number of elements in each of the clusters are equal. So the last lecture set dealt with a special case of cluster sampling where we have equally sized clusters, and from that, how we can effectively use an approximation to the ANOVA procedure, or how we can frame the problem in the context of an ANOVA, and we can build an estimate for our SRS estimator and then compute the relative efficiency of the cluster sampling approach to the simple random sampling approach using the same sample. Now again, this is a very interesting and helpful idea because when we introduced relative efficiency at the end of lecture set 4, one of the comments that we made was this works best when using the same sample. So if we wanted to compare the simple random sample estimator of the mean to the ratio estimator of the mean, we would want to use the same data to do that because otherwise the comparison could be unfair. For example, if my simple random sample estimator used a sample size of 20 and my ratio estimator used, a sample size of even 25, that little extra information could lead to a decrease in the variance of the estimator, which could result in us saying the ratio estimator is the more efficient estimator, when in reality it might actually be the other way around. All right. Okay, so today we're going to pick up with a second example of sample size calculation. So that was the last thing that we talked about on Friday. So the example given or the first example given on slide 18, this is basically just the traditional sample size style calculation for any of the sampling approaches that we've seen in the course. So for example, on slide 18 here, we're basically asking how many clusters do we need in order to estimate the total error. Well, in order to bound our estimate for the mean, it looks like in this case, within two units. So this is basically just the standard rearrangement of the variance of the mean estimator, which you can see starting at sort of the bottom of slide 17 here. And then that gives us our sample size calculation. And then, we're just plugging in from that point on to show that we need, in this particular case, 13 clusters. Okay. The second illustration uses the second approach that we discussed last class for estimating a population quantity. Or sorry, that we discussed on Wednesday for estimating a population quantity. So in this illustration, we're going to be using the formulas given on slide number, here it is. So basically in this illustration, we're using the formula given in equation 3 here. So we want to estimate so we want to estimate the total. So in this illustration on slide 10, we have use 3 to estimate the total amount spent by the 96 industries described in example 1. Place a bound on the error of estimation. So in this second sample size calculation, we want to estimate the total within 2 units. But in this case, we're going to bound using what's given in equation 3 rather than rather than using what was given in equation 1 or equation 2, I think it was, for the total on, equation 2 for the total on slide 8. So pretty much the same problem that we saw in exercise 1. We're just bounding using a different formula in this case. And the rationale again here is that we don't actually have the total number of population elements, right? So in this case, so we can make a little note. So assume capital M is unknown. Right? So recall that the variance of mu tilde t is equal to 1 minus little n over capital N multiplied by sigma squared t over little n. Right? Okay, so our bound is equal to 1.96 multiplied by the square root of 1 minus little n over capital N times sigma squared t over little n. Okay. And now basically you can see that this is the exact style of rearrangement that we've been used to whenever we've done sample size calculations for SRS. So it's pretty easy to show, following what we've done before, that this thing is going to become the bound squared divided by 1.96 squared sigma squared t multiplied by n squared. Oh yeah, missing an n squared here. Total multiplied by n squared plus 1 over n inverse. Right, so hopefully that looks familiar to you. Again, this is a rearrangement that we've done on a couple of occasions already. So this form is something that we should hopefully recognize at this point because we've seen it in the SRS case and we've seen it in the even in the systematic sampling case because those use SRS. And we had similar forms when we wanted to break down each of the different strata components as well. So those ones are obviously a bit more calculated because we had to have the sums across the strata, weights and whatnot involved. Okay, so this is going to give us 2 squared divided by 1.96 squared multiplied by 0.083 multiplied by 96 squared plus 1 over 96 inverse. And that gives us 84.9049. And then from there, n is approximately 85. So we don't need to say approximately, we can say use n equals 85 clusters. All right. So again, just another sample size calculation based off of the cluster sampling approach. We've now seen 2 sample size calculations. So as you will recall, when we first introduced cluster sampling, and I talked about this at the start of class, we had 2 different approaches for estimating the total of the variable of interest. One that requires that we know the number of elements in the population, capital M, and one that requires that we do not. In the first illustration, we did the sample size calculation using the formula that requires that we have capital M, or at least that we can estimate it. In the second illustration, assuming that we don't have any information about the total number of elements in the population, this would be another way for us to arrive at an estimate for the quantity of interest, which here is actually the total. All right. Okay, so what we're going to talk about next is proportion estimation within cluster sampling. After we talk about proportion estimation within cluster sampling, we are then going to talk about stratification within cluster sampling. And then time permitting, we'll talk about we'll introduce 2-stage cluster sampling. Each of these ideas, again, are essentially just extensions of what we saw before. So given that we understand how a cluster sample is collected, what a cluster sample is, it makes sense that we can take each of the different approaches that we studied in, for example, simple random sampling, and plug those ideas into a cluster sampling context. This was the same thing we did with stratification. And actually, again, as you will see in a little bit, we can combine the idea of cluster sampling and stratification into one idea where we stratify within each of the clusters. All right. So starting off with proportion estimation within the context of cluster sampling. If we want to estimate some population proportion, which we can actually call pi, not p, we can use the following estimators. Pi tilde is the sum of ai from I equals 1 to n, and the numerator here is, pi tilde is equal to the sum from I equals 1 to the number of clusters of the ai divided by the sum from the sum from 1 to the number of clusters of the mi. So the ai is effectively going to be some value that would have minimum 0, maximum mi, right? So the ai here would be between 0 and mi, because the ai is effectively like a binomial random variable. It sums the number of ones for every single element in the population. So in this particular instance, each observation within each cluster is contributing a 0 or a 1, depending on the question that we are asking. So if we were to say, like, I mean, just in a simple case, like answer yes or no to the following question, yes is a 1, 0 is a no, we're going to have a set of binary values within each cluster, so ones and zeros. And the AI is just, each AI is the sum of all of those ones and zeros. So our proportion estimate is simply going to be the sum of all of the people that answered, well, that gave the answer corresponding to a 1 within each cluster across the clusters, divided by the total number of people across all of the sample clusters. And then the variance for our proportion estimator is going to be very similar to what we saw before. So we have 1 minus n over little n, so the FPC, multiplied by the variance estimator for the proportion divided by n times m bar squared, where m bar squared, again, is going to be the average of the number of elements across all clusters in the population. And you can see the form of sigma hat squared pi hat shown below here. So we have the sum of the AI minus pi I times mi squared over n minus 1 in that case. All right. Now we have a note that the variance of this estimator is only good, where good can mean a number of things, when the number of clusters is at least equal to 20. Further, just like with our estimator for the mean and the total, if the cluster sizes are equivalent, then the estimators in 13 are unbiased. Okay, so to illustrate the proportion approach, we have the following example. A newspaper wants to estimate the number of voters favoring a certain candidate. A sample of 50 precincts is selected from 497. All right, so first off, let's just make a note of a few of the things that we know here. We know that capital N is equal to 497. Okay, so we're treating the precincts as the clusters. So we have 497 clusters, and we have collected a sample of 50 of those clusters. Right? Within each of the sampled precincts, we have the total number of voters. So this is going to be the MI. So those are the number of observations within each cluster. And then each of the persons in favor are going to be the AI. So the A subscript I, again, sum or count the number of people that have contributed a 1 in the context of the problem. So in this particular case, we're basically asking, are you in favor or against, or are you in favor or not in favor of a certain candidate? There's 680 of 1,290 people in the first precinct that are in favor. Okay, so the 680 counts the number of people that said, yes, I am in favor of this candidate within that precinct. And that's consistent across all of the different precincts, which we are calling clusters in this particular case. All right, at the end of the rows, we have the sums. So this here is going to be the sum from I equals 1 to n of the mi. And this here is going to be the sum from I equals 1 to n of the ai. So those are the two major quantities that we need for estimating pi. All right, so in part A, when we're asked to actually estimate this value, we would have the following calculation. Pi hat is equal to the sum from I equals 1 to little n of ai divided by the sum from I equals 1 to n of the mi. Right? So that gives us 44,136 divided by 77,419. And that gives us 0.5701. All right, in part 2, we're just asked to place a bound on this estimate. Okay, so the bound here is just going to be 1.96 multiplied by the square root of the variance of pi tilde. So that's going to be 1.96 multiplied by the square root 1 minus little n over capital N sigma hat pi over n. 1.96 multiplied by 1 minus 50 over 497 multiplied by 31,377.58371 divided by 50. And that gives us, oh, shit, divided by 50. Okay, and then we need our estimate of m bar squared in this case. Okay. Squared. Okay, and then to get this, what we should be able to do is just take the sum of the mi and divide by 50. I'm just going to check that real quick back. So here, for the m bar squared, use little m bar squared is the sum from I equals 1 to n of the mi over n, which is equal to 77,419 over 50, which is equal to 1,548.38. Okay, so here we now have 1,548.38 squared. Okay, and that should give us 0.0300731. Yeah, you can write the FPC check, but in this case, it's pretty obvious that you're going to have to use it because 50 over 497 is not going to be less than 0.05, but we can still write it. So never enough room. All right, so for the FPC, just to clarify, we have 1 minus 50 over 497, which is 0.899. Okay, so therefore we have to use it. Okay. Any questions? Any other questions? Okay, so again, just for clarity, just to recap, what we've basically done so far is just the sample size calculation for the total when we don't have capital M, and we have done capital M is the total number of elements in the population, and we've now done an example of how to estimate a population proportion using cluster sampling and bound that estimate. So of course, if we wanted to turn this into an interval, we would just take 0.57 and add and subtract 0.03007. Exercise number 2 or example number 2 states or asks how large a sample size would be required to estimate the proportion of voters favoring the candidate to within 0.057. So we have B is equal to 1.96 multiplied by the square root of 1 minus little n over capital N times sigma squared pi over little n, right? Okay, so this is going to give us, following the same logic that we had before, this is going to give us b squared over 1.96 multiplied, oh, I always forget the m bar squared, multiplied by m bar squared, multiplied by sigma hat squared pi. Actually, sorry, let's just take a look at this for a second because you would have n, you'd have m bar squared. That's definitely there. No, there's something, sorry, one sec. Let's just take a quick look at this. So you'd have b squared over 1.96 squared is equal to 1 minus little n over capital N times sigma hat squared pi over n m bar squared. So that's going to give you b squared m squared. Yeah, okay, that makes more sense. 6 squared sigma hat squared pi is equal to 1 over n minus 1 over n. Yeah, okay. So then that's going to give us n is equal to b squared m bar squared over 1.96 squared sigma hat squared pi plus 1 over n inverse. All right, so we need again a few values here. So m bar squared, or for m bar, use little m bar, which was 1,548.38. Okay, for sigma hat pi, use an estimate. Okay, so for example, we can use what we calculated in the previous questions. use sigma hat squared pi is equal to 31,377.58371. But this value, for clarity, that could, like in a situation where, for example, we didn't have the data given to us. So imagine that we had the same type of question, like how large a sample would be required to estimate this proportion within a certain bound. The value for sigma hat squared pi could also come from previous information. So maybe a pilot study that was run beforehand that suggested that this is where the variance should be. So in this case, we're basing it off of the information that we have in the example that we're working with. But in a situation where we do not have the raw data and we're not able to calculate this value directly, this could come from, for example, again, like a previous study of the same quantity. Okay, so if we plug each of the values in, we should get 0.05 squared, 1,548.38 squared divided by 1.96 squared multiplied by 31,377.58371 plus 1 over 497 inverse and then that should give us 16.627. So therefore, use n equals 17. All right. Okay, so again, we've seen sample size calculation for a population quantity using either of the two approaches that we talked about for estimating, well, in this case, the total based off cluster sampling. And now we have seen estimation of a population proportion using cluster sampling and the sample size calculation for the number of clusters that would follow from, or that we would utilize if we were working with a proportion estimate. Okay, now what we're going to talk about is the amalgamation of cluster sampling and stratification. So when we use cluster sampling and stratification, I misspoke at the beginning because I said you would select a cluster then stratify within. It's actually the other way around. So what we would do is we would stratify the population into different clusters, or we would stratify the population into different strata. And then within each of the strata, we can take a cluster sample. So again, the idea with cluster sampling is instead of selecting individual units, we are selecting collections of units via basically just a simple random sampling protocol. So it follows more naturally then that if we take a population of interest and we separate it into different regions, for example, where each region could be the strata that we are interested in working with, then within each of those strata, instead of doing a traditional SRS, we can select clusters of observations using cluster sampling. Okay, so the estimator for the population mean via cluster sampling is effectively a ratio estimator, where you have the sum of the variable of interest divided by the sum of the number of observations across each of the clusters. In lecture set 4, in the last example of lecture set 4, we talked about the two different ratio estimation approaches within stratification. So we had the separate estimator or the combined estimator. The separate estimator requires that we have the number of population elements, capital M. Okay, so it makes sense that we will focus on then the combined ratio estimator because that does not require us to know how many elements are actually within each of the strata and then within the total population that we are working with. So again, here the idea is stratify and then cluster. Okay, so if we have a population that has been divided into H different strata, we can estimate the population mean using the sum across the strata of the number of clusters, right? So our capital NH here is number of clusters within strata H. So we have the sum of the number of clusters within strata H multiplied by the mean estimator within that strata, where the mean estimator here uses the second formulation that we talked about for cluster sampling. So we have the sum from H equals 1 to little nh of the YH over little nh. And then we divide by the sum from H equals 1 to capital H of nh multiplied by little m bar h squared, which we can estimate using our information from the strata, right? So number of clusters. Okay, and then you can see from the definition below, this is mean for strata H, and this is average number of elements per cluster within strata H. Right? And then you can see that our variance estimator is going to be pretty similar to what we had in the stratification case. So we have 1 over m squared, which is the total number of elements within the entire study, but we're going to estimate that using little m, which is the sum from h equals 1 to h of nh over little m bar h squared, or little m bar h. And then we're basically just multiplying our FPC for the cluster sample by nh squared, and we're summing across each of the different strata. All right. Okay, so to illustrate this approach, we have the following data set. So we have 80 retail stores in Florida, and we have 140 retail stores in California. The number of sick days taken by employees were counted at a number of different locations. Okay, so we have capital N1 equals 80. So 80 stores, each store forms the cluster. Capital N2 is equal to 140. Okay. And then this is given that H is equal to 2, which is Florida and California. Right, so we have 2 strata, which are the regions, the states. And then within each of the strata, we have 2 different clusters. Or within each of the strata, we have 80. Within strata 1, we have 80 clusters that are possible. And within strata 2, we have 140 clusters that are possible. Okay, now if we look at the data, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so that means that little n1 is equal to 8 and little n2 is equal to 10. So we have 8 clusters from the Florida state, or from Florida, and then we have 10 clusters from California. Okay, so the MI count the total number of observations, or the number of observations per cluster, right? So this value here, maybe I should write it like this. Right, so we have the sum from 1. So we have the sum from I equals 1 to little nh to little n1 of the mi is equal to 109. The sum from I equals 1 to little n2 of the mi is equal to 144. And then we have the sum from I equals 1 to little n1 of the yi equals 337. and the sum from I equals 1 to little n2 of the yi equals 355. Okay, so we want to estimate the average number or the average amount of sick days per employee, and we want to place a bound on the error of estimation. All right, so for part A, we're going to use our mean estimator. So we're going to have mu hat C, what did I call it? CS, C comma S? Yeah, mu hat C comma S is equal to the sum from H equals 1 to capital H of capital NH multiplied by mu hat TH divided by the sum from H equals 1 to capital H of NH multiplied by M bar H. All right, so this is going to give us 80 multiplied by, and then we're going to have the sum from I equals 1 to little n1. So that's 337 divided by the number of clusters, little 8. And that's because, again, the mu hat t that we're using is the sum of yi over n for each of the different strata. And then that's going to be added to 140 multiplied by 355 over 10. Okay, and then in the denominator, we'll have a similar calculation, but in this case, we're taking the average for each of the sample sizes, like that. And that gives us 2.685. Right. Okay, so in part B, we have okay, so here we're going to have the variance of mu tilde CS is equal to this 1 over m squared multiplied by the sum from H equals 1 to capital H, 1 minus little n H over capital NH. NH squared multiplied by sigma hat, what did I call this one? C comma H, okay, sigma hat squared C comma H divided by little NH. Okay, so we have a few different things that we need to work out here, right? So first off, we're going to replace this with the estimate from the previous slide. So this is going to become little m squared. Now inside here, we're going to have capital N1 squared, 1 minus little n1 over capital M1 multiplied by sigma hat squared C1 divided by little n1 plus n2 squared, 1 minus little n2 over capital N2, sigma hat squared C2 over little n2. Okay, so we can check each of these, right? So this is going to be 1 minus 10 over, or 1 minus 8 over 80. Maybe I shouldn't do it here just because of the inline part. Right, so if we do that, so we have FPCs. So for H equals 1, we have 1 minus 8 over 80, which is equal to 0.9. And then for H equals 2, we have 1 minus 10 over 140, which is equal to 0.939. Right, so you can see that we need the FPCs for each part. Okay, now we also require these sigma hat squared terms. So first, M is equal to the sum from H equals 1 to capital H of NH multiplied by M bar H. So that's going to be 80 multiplied by 109 over 8 plus 140 multiplied by 144 over 10. Which is equal to 3,106. Okay, so we also need the sigma hat squared C1. So that's going to be the sum from I equals 1 to little n1 of the yi minus mu hat c mi1 squared. Right, and that's going to give us 58.94969. And then we also need the same measurement for the second cluster, or for the second strata. No, it would be for the cluster. So this would be yi2 minus mu hat c mi2 squared. And that gives us 298.2907. All right, and then if we plug this information into the above, we should be able to show that this quantity works out to be in the area of 0.06067364, which means that the bound, which is 1.96, multiplied by the square root of the variance of mu tilde CS, should be equal to 0.4828. All right, sorry, I went a little bit over there. Okay, so that's the example of stratification and cluster sampling together. So on Wednesday, we'll start talking about two-stage cluster sampling, which is the next extension of this work. On Friday, we'll probably introduce sampling with unequal weights. So how we perform estimation and in the situation where we don't assign equal weight to every observation in the population. And then on Monday, we will have our third quiz, which covers post-stratification through lecture set 4. And I posted the exact slide numbers for that on Friday in the announcement for the end of last week. So as always, if you guys have any questions, please let me know. And otherwise, I will talk to you on Wednesday.